Okay, welcome to this the second session. So I was going to talk to you a little bit today about algebraic numbers. Now, if you have an equation of the form ax squared plus bx plus c equals 0, so this is a polynomial, and you're looking for the roots of that polynomial, then we know that you can write the roots as what is it? No, it's no. See, it's wait. What is this? It's what is it again? Minus b, plus or minus this over 2a. Yeah. Gosh, that's a good start. Thank you. Now. And this is because that's a second degree polynomial. If you had the third degree polynomial, there's an equation. I'm sure you all know it, so I'm not going to attempt. And the fourth degree polynomial, Moshe, I'm sure you do. Okay. And what everybody knows is that there is no equation for fifth degree polynomial, right? And actually, if you, in algebraic number theory, this is actually a very minor result, right? It's a result everybody knows, but it's actually a result that's of relatively little consequence. It's a sort of a non-result. I mean, don't put it on too much. But so what happens is the result says that if you have a polynomial, the first lower bound. Really? Okay, interesting. So I hadn't thought about that particular angle. What about the irrationality of square root of 2? I think that's a good contender. Yeah. So now what it says that if p is a polynomial of degree 5, then you cannot write the and alpha is a root of p of alpha is equal to 0. You cannot always write alpha as a function of taking roots. Kth roots of numbers, taking combinations, plus, minus, divides, multiplication, so on. You cannot always express the roots in terms of, this signature. But of course the roots exist, they're algebraic numbers, and in fact there are other representation of these roots that you can manipulate and so on and so forth. So it's sort of a historical accident that we focused on, extracting kth roots and really being obsessed by this. Because if you forget about this, then the theory of algebraic number actually works very nicely. You can almost think of the algebraic numbers as rational. So I'm going to try to explain what I mean. And so how would you represent an algebraic number? So if you have a polynomial, so p is a polynomial. Okay, so with integer coefficients. And you have p, so let's say you have p of alpha is equal to 0. So alpha is an algebraic number. So I'm writing algebraic numbers as a closure, the algebraic closure of the rationals, and these are complex numbers in general. And you want to find a way to represent alpha, okay? Now the thing is, this polynomial p may have several roots, as many of its degree as is well known. And so, alpha may be here, maybe, beta is another root, and so on, right? This is the complex plane. So how could you canonically represent roots and manipulate roots? Well, first of all, so one way to do it is to have an approximation of the root. And so, for instance, you could represent a root with two rational numbers a and b, and so you've got a, you've got b, and you've got r. So these would be rational numbers, and you would say that alpha is the unique. Sorry, you've got ab is here, alpha maybe is here, and r, and that's r. So alpha is the unique root of the polynomial p that is within distance r of the point, and this is the point a plus bi. Okay? And that way of representing rational actually makes sense. So in order to represent the rational numbers, you need to have, algebraic numbers, you need to have, the polynomial p. And rational, so this is in, this is actually, I'm going to write it in q of x. And I want p to be the minimal monic polynomial such that p of alpha is equal to 0. Okay, so there may be many polynomials p such that p of alpha is equal to 0, but there is always going to be one of minimal degree, and then I just, by monic, I just want to say that the coefficient of the highest degree term is 1. Okay, so then it uniquely defines it. And you can compute all these things, right? You can, so there are algorithms to compute these things. If I give you a polynomial such that alpha is a root, you can actually extract from this polynomial the minimal polynomial of alpha. So I don't want to talk about these algorithms. And then you need to know how do you choose these ABR. And for this, you can use the following fact, that if alpha and beta are roots of the same polynomial, so this is for any polynomial p with integer rational coefficients. Yeah, let's say for with integer coefficients. So the degree of p is the degree of the exponent of the highest exponent you have to a variable, and the height. So everybody knows the degree, and the height of p, which I write also h of p. This is the maximum of the absolute values of the coefficients of p. So in other words, if p is a0 plus a1x plus ... plus ak x to the k, then the height of p is going to be the maximum of a0 in absolute value ak, and the degree of p is going to be equal to k, assuming that the term ak is not 0. Okay, does that make sense? So I've got a polynomial like this, and it doesn't have to be minimal, and I'm telling you that p of alpha equals p of beta equals 0. So alpha and beta are both roots of p. Then there's some bounds, which I'm not going to prove, but they're elementary bounds. And the result, I'm going to just state as a proposition. This is due to Maurice Mignot. If alpha is not equal to beta, then there's a separation, minimum separation between alpha and beta. They cannot be too close to each other. And that's bigger than square root of 6 divided by d to the d plus 1 over 2 times h to the d minus 1. Don't know if sorry? Sorry, d is the degree. D is the degree of the polynomial. Yes, which I call k here. So yes, sorry. D is more natural. I mean, the bound is usually, so h is the height and d is the degree. Okay. Two distinct roots, exactly. So let me just ask you as an exercise. I give you a polynomial p. Okay. I give you a polynomial p with height h and degree d. Okay. And suppose that I tell you that p of alpha is equal to 0 and that alpha is not equal to 0. Then can you give me a bound on the absolute value, the modulus of alpha? So what I'd like is a lower bound. I want to say alpha is bigger, in absolute value alpha is bigger than something. How could I do that? It assumes nothing. Very good. So you consider the polynomial q of x, which is defined by x p of x. And you have that q of alpha is equal to q of 0 is equal to 0. Now, the degree of q is 1 more than the degree of p. The height of q is clearly the same as the height of p. So h doesn't change, but in this formula here, d becomes d plus, d increases by 1. So you just use this bound with the d being increased by 1. Okay, does that make sense? So this is how you can use these sorts of bounds. Okay, so now that I have this, then if I have a polynomial p, and I want to represent one of its roots, then all I have to do is make sure that the radius is in question is less than, say, 1/4 of this minimal separation. And then no matter what, as long as I say alpha is the unique root that is within distance r of the point a plus bi, I have uniquely identified alpha, thanks to the separation result. Does that make sense? So that's a representation. It's called canonical representation. Of course, it's not unique because, if you take a smaller r, then this will also be a representation. It's called canonical representation. And with this representation, you can now do things such as you have a representation for alpha, you have a representation for beta, and you want to compute a representation for alpha plus beta, where alpha and beta are just two algebraic numbers. Then you can compute in polynomial time a representation for this, a representation for alpha times beta, a representation for the real part of alpha, a representation for, what have you, right? 1 over alpha, assuming alpha is not 0, and so on and so forth. You can do all this arithmetic, and you can represent these numbers using this representation. So in particular, if it's a 5th degree polynomial that has roots that are not expressible as radical, that absolutely doesn't matter. You can just use this representation that just works seamlessly. Okay, does that make sense? Now, using this representation, you can also test. There are algorithms. This is all polynomial time. You can do all these things polynomial time. Not that this really matters. You can decide, for instance, if, you can decide if alpha is equal to beta. That's fairly easy. They need to have the same minimal polynomial, and then you check whether they're the same root, and so on. You can decide if the real part of alpha is bigger than the real part of beta. You can decide, is alpha a real number? You can decide all these things. I'm not going to prove this. You know these things are decidable. Yeah. Now we're going to assume that rational numbers are represented like this. Algebraic numbers. Thank you, Moshe. I just. You can answer all these questions. Now, you always knew you could answer these questions because you can always phrase these questions in the existential theory of the real. So you can say, I have a polynomial such that blah, blah, blah. Is it the case that this polynomial is real? Because you represent a complex number as a tuple, the real part, the imaginary part, and so on. You could do this in the existential theory of the reals. That would give it to you in p-space. I'm claiming you can do these things in polynomial time. And so I'm lying a little bit. What you have to do is you've got to assume a base number field where you're working with you're working in a number field which is the field extension of Q with a certain number of algebraic numbers. Now, any operation you do on these algebraic number remains in this field, okay? By definition of a field, and all the operations are now in polynomial time, as parameterized by these numbers. If now all of a sudden you want to throw in an additional number, this means, if you keep adding new numbers, this will not say in polynomial time necessarily. But if you're working in this field for fixed algebraic numbers, which we do, then everything is polynomial time. Okay, does that make sense? Okay, so that's for algebraic numbers. I will just say one more thing, which is there's an operation. So I want you to think of algebraic numbers as rational numbers. Probably why I keep making this mistake. So basically, you can do all the arithmetic you can do on them. You can decide. You can, sometimes people, when I talk about these things, sometimes people say, "Oh, how can you decide these algebraic numbers? How do you know if they're, we're just going to assume now we can do all this arithmetic exactly, manipulate them as if they were rational." There is one thing though. Suppose you want to know, is there an n such that alpha to the n is equal to beta. So I'm giving you alpha and beta, and I want to know if, or even instead of beta, let me just say 1, for instance. I want to know if alpha is a root of unity, or if alpha to the n is equal to beta. This is not completely obvious that you can do this. This can be done. And just very, very quickly try to give you an intuition why. So you want to know if alpha to the n is equal to 1. Now, if your alpha is a number of modulus strictly greater than 1, the answer is going to be no, because as you keep multiplying alpha with itself, its modulus will increase. And likewise, if alpha is of modulus strictly less than 1, then alpha to the n is always going to be of modulus less than 1. So the tricky part is when alpha actually lies on the unit circle. And now it's kind of, you can't use a growth argument. And here what you need to use, I mean, there are a few tricks. And I mean, this is all sort of standard basic algebraic number theory. And it uses a bit of Galois theory, but there's a few tricks. So basically, you cannot use the you want to use a norm argument, but you cannot use the Euclidean norm. The Euclidean norm works when alpha is bigger than 1, then it keeps growing, right? So the Euclidean norm at that point is going to work. You have to use a so-called p-adic norm. So you have to use, yeah. No, it doesn't have to be. You could have a polynomial of a smaller degree, and it happens to be a root of unity. So you could have a minimal polynomial. Yeah, it doesn't have to be. Otherwise, yes, that would be, yeah. You could have a fluke coincidence of a polynomial of lower degree, which actually has roots that are roots of unity, right? Nothing prevents that. I mean, you're right that this is a polynomial, but that polynomial could factor potentially. Now, what you can use, I'm going to describe, because I'm going to be using p-adic analysis in just a little while. So let me just hold this thought for a sec, and let's just look at. I'm just going to look at integers for the time being. So suppose you take a number r, which is an integer. And you take p, which is a prime, then I want to define the p-adic valuation of r. And the p-adic valuation of a number r is going to be 0 if the prime p does not divide r. Is going to be k if p to the k divides r, but p to the k plus 1 does not divide r. So k is the largest power of p that divides r. And it's going to be infinite if r is equal to 0. And the reason is that p to the arbitrarily high will obviously divide 0. Okay? So the p-adic valuation of an integer. Okay? So it's a function v. So p is a prime. Okay, so I fix p actually. Then I give you an integer r. And the p-adic valuation of r is defined by this. And it's the largest power of p that divides the number. Okay? And you can define the p-adic valuation. Now you can extend this to rational. So let's say r over s. And the p-adic valuation of a rational is defined to be the p-adic valuation of r minus the p-adic valuation of s. And you can show this is well defined. Does not depend on the representation. Okay, and this p-adic norm is this p-adic norm is what you define the p-adic rationals and so on. There's a whole field dedicated to studying. I mean, there's p-adic analysis and p-adic number theory and so on. This p-adic norm becomes extremely useful when you cannot use the Euclidean norm. And in number theory, very often you'll have a theorem stated in terms of the norm of this, goes to 0 or something, and then you'll have an equivalent theorem saying the p-adic norm of this behaves in this way. Here, in particular, you can extend this theory of, so I'm just giving you, I mean, we're going to come back to this, but you can extend this theory of a p-adic norm not just to integers and rationals, but to algebraic numbers. Yeah, so yes, no, let me talk about just the p-adic valuation. Yes. You can extend this theory to algebraic numbers. Then you have to talk about, you don't talk about primes, you talk about, you move to ideals. But the idea is the following. If you want to know whether alpha to the n is equal to 1, you find an ideal such that the p-adic valuation of alpha is greater than 0. Okay? And you now, this is more relevant if you're trying to decide if alpha to the n is equal to beta. So the p-adic valuation of alpha is greater than 0. And now basically the p-adic valuation of alpha to the n is going to be equal to n times the p-adic valuation of alpha. This is obvious in the context of integers, right? I mean, the p-adic valuation, in general, the p-adic valuation of r times s is going to be the p-adic valuation of r plus the p-adic valuation of s. And you simply evaluate the p-adic valuation now of beta. It's going to be some number. And then this places a bound on n, according to which, after which alpha to the n cannot be equal to beta because this grows. Okay, so basically you have to, in order to decide certain things about algebraic numbers, you've got to sometimes use arguments that involve the Euclidean norm, sometimes arguments that involve the p-adic norm. But let's, that's all I want to say about algebraic numbers. And I'm going to, but we'll be coming back to this p-adic valuation business over the integers and rationals. This will play a prominent role in a short while. Let me say one more thing since I've defined it here. So this is one property. Does everybody see this? The p-adic valuation of a product of two integers, or for that matter, two rational numbers, is the sum of their p-adic. And you have another property, the p-adic valuation of, let's say, a plus b. What can I say about this? The p-adic valuation of a plus b, it's at least the minimum of the p-adic valuation of a, and the minimum of the p-adic valuation of a and the p-adic valuation of b. Okay, does everybody see this? If let's say the p-adic valuation of a is k, and the p-adic valuation of b is k plus t or something like this, then a plus b is definitely divisible by p to the k, because a is divisible by p to the k and b is divisible by p to the k, in fact, even further. So their sum will be divisible at least by p to the k. Okay, so we'll be using these things later on. Any questions about manipulation of algebraic numbers? Yeah. Yeah, I haven't even told you what that means, because you're not talking about primes now. You're talking about prime ideals. So I mean, I would need to define this. This is sort of the sort of things that you find in books on algebraic number theory. I mean, this is sort of it came about, by the way, because unique factorization fails for algebraic numbers. But it's recovered once you move to ideals. So there's always a unique factorization of algebraic numbers as a product of prime ideals of algebraic numbers. So this is how this whole field began. So, I mean, just to give you an example, you can write 10 as 2 times 5, and you can also write 10 as something like 2 minus root 6. Sorry, 2 minus root of minus 6, 2 plus root of minus 6, right? So you have two prime factorizations for 10. If you go in the right number field, you can have 2 times 5, because this is not right? Yeah, this is right, isn't it? 2 minus square root of minus 6 times 2 plus square root of minus 6. Both these products give you 10. And you can show that this is an algebraic integer, this is an algebraic integer. In the right number field, these are going to be irreducible, so you don't have unique factorizations. This is how this whole theory of algebraic ideals came about. But I'm not going to say more about this. Just take my word for it that you can do arithmetic on algebraic numbers, because that's all we're going to be using. Okay. Let me describe something else. So you remember, I'm in the complex plane again, and you remember that we had a number lambda 1. So lambda 1 is a complex number of modulus 1, and not a root of unity, okay? And if we look at the iterates, lambda 1 squared, lambda 1 cube, etc., the infinite set of the powers of the lambdas, we said that this set here was dense on the unit circle. Okay, in fact we proved that yesterday. You remember? Okay, so suppose you've got this, and suppose you've got here lambda 2, and so lambda 2 is also of magnitude 1, not a root of unity. So lambda 2 to the n, okay, this set is dense in the unit circle, okay? And now, what about the joint density? What do you think happens if I'm looking, so if I write T for the set of Z, the set of complex numbers Z that have magnitude 1. So T is the one-dimensional torus. So this is the circle, the unit circle, yeah, in the complex plane. So I know that the set lambda 1 to the n, I know that this set is dense in T, and I know that the set lambda 2 to the n is dense in T. And I'm wondering, what of the set lambda 1 to the n, comma, lambda 2 to the n, so same n. Okay, so I'm looking at this set now. It's clearly a subset of T cross T. Okay, but is it dense in T cross T, right? I mean, that's a natural question. Any guesses? What's that? Not always. So obviously not always, because in particular, if lambda 2 is equal to lambda 1, then, well, it's obvious that, whatever this guy is determines that guy and so on. But more generally, if there exists algebraic, so first of all, how would you represent T cross T? What would be a good representation of T cross T if you're drawing something? It's a torus, right? It's the two-dimensional torus, so it'd be something like this. Everybody sees why this is a representation cross T. So, one circle is like this and the other circle is like that, right? So what we're saying is that in some cases, the iterates, they're going to be dotting this torus densely. But in other cases, they're going to be dense in some kind of helix on this torus, but not dense everywhere. And that happens if there's some algebraic relationship. So in particular, if something like lambda 1 cubed times lambda 2 to the 7 is equal to 1. If you have a relationship of that nature, then you're not going to be dense in the circle because of this relationship. So it turns out, now you would like to elicit all such relationships, and this is something that's actually a very deep result due to Masseur. So theorem, well, actually, before I state the theorem, let me state the definition. So let lambda 1, lambda k belong to be algebraic numbers of modulus 1. Then I want to look at the set L, which is the set of all integers n1 dot dot dot. Maybe n1 is not so good. Let me call it, let's say, s1 dot 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 sk, such that lambda 1, so these are integers in z to the k, such that lambda 1 to the s1 times dot 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 times lambda k to the sk is equal to 1. Okay? I want to look at this set. What kind of set is this? It's a lattice, yeah, very good. I bet people don't even know what a lattice is. That's a little bit too advanced. So it's a group. It's an abelian group. If you take S1 to SK, that has this property, and you take S1 prime to SK prime, that has this property, and you add them, then you again get a tuple of number that will have this property. And that is going to be clear because when you work it out, you're going to get lambda, it's going to be clear because you're going to end up with 1 times 1 equals 1, basically. Okay. So this is actually a Z module, or equivalently a free abelian group. And it has a basis. So L has a basis. Which can be computed, and it turns out in polynomial time. So, but we're not gonna use this. And this is a deep theorem that follows from results of Masser. This is very much non-trivial. Okay, but we can get our hands on this. And using that result, and I'll come back to this later on, we can actually find the subtorus of t to the k, upon which the iterates are actually dense. Okay, I'll be revisiting this later on. Okay, so but does this make sense? What I've talked about right now? Okay, you'll see there's method in the madness. Why am I talking about all these crazy things? And the reason I'm talking about these crazy things is that I want to talk to you about solutions of linear recurrent sequences. We come back to the object that we first encountered, and that's linear recurrent sequences. So let un n equals 1 to infinity be a linear recurrent sequence over, let's say, the integers, given by u n plus k is equal to a1 u n plus k minus 1 plus dot 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 plus ak times un. Okay. So now I want to define the characteristic polynomial of un is p of x is equal to, and I read it from the recurrence relation. So it's going to be defined by x to the k minus a1 x to the k minus 1 minus a2 x to the k minus 2 minus dot 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 minus a k minus 1 x minus ak. Okay, that's the characteristic polynomial. And you remember that linear recurrent sequences could always be expressed in matricial form, right? As a V transpose m to the n w. This characteristic polynomial is actually the characteristic polynomial of that matrix. So I'm interested in the roots of the characteristic polynomial, which equivalently would be the eigenvalues of the matrix. So let lambda 1 up to lambda m be the distinct roots of P. So by distinct, I mean these roots could be repeated. I'm just taking one copy of each of the roots, right? So if a root is repeated, I'm not ignoring that, but if lambda 1 is repeated 3 times, I'm just listing lambda 1 once here. So now I'm assuming that I've got m. So m may be different from k is what I'm saying, because there may be repeated roots. Now it turns out that un can always be written for all n as a summation for j equals 1 to m of polynomials of the form pj of n times lambda j to the n, where each polynomial pj is a polynomial with algebraic coefficients. Okay? So the case of Fibonacci, if you remember, so for the Fibonacci sequence, we had that, so Fibonacci, we had that un was equal to 1 over root 5 times 1 plus root 5 over 2 to the n minus 1 over root 5, 1 plus root 5 over 2, 1 minus root 5 over 2 to the n. So here, the eigenvalues, that's the lambda 1, that's the lambda 2, both real. And these constants, 1 over root 5 and minus 1 over root 5, they're actually the polynomials. In fact, the degree of the polynomial pj will be equal to the multiplicity of the corresponding characteristic of lambda j minus 1. Okay? So if lambda j is a simple root, the degree of the corresponding polynomial pj is 0. In other words, pj is just a constant. So this is the case of Fibonacci. Okay, does this make sense? Okay. This may look a bit mysterious. So this can be, obviously this can be proven. I'm not going to prove it in detail. It's a little bit annoying. The sort of canonical way to prove it is to notice that, of course, the eigenvalues are solutions of by definition, the characteristic root is a solution of this polynomial. And therefore, the characteristic roots naturally satisfy this equation. And now the set of solutions of a linear recurrent sequence actually forms a vector space, and so you basically proceed from there. But let me give you another proof of this fact, which is perhaps more intuitive. So recall that un could be written as v transpose m to the n w for some vector v, w, and a matrix m. Okay, we did this yesterday. Okay, now so this being the case, so any matrix m can be put in Jordan normal form. So I can write un as v transpose p inverse. Now I've got j to the n times p times w. So here p inverse j to the n p is simply m to the n, because j is the Jordan canonical form of m. If you've forgotten your linear algebra, just bear with me 5 minutes. This is not super important. I'm sort of just giving you an argument why this is true, and you can just take it on faith afterwards. But if you remember enough, then so what does this matrix J look like? This matrix J, it's a matrix of the following nature. You will have the eigenvalues on the diagonal, so you'll have lambda 1, let's say lambda 1, and then more eigenvalues, lambda 2, and so on. And on the super diagonal, you will have 1s. So here you will have, let's say, if lambda 1 is repeated 3 times, you will have a Jordan block of the form lambda 1, lambda 1, lambda 1, and when 2 1s on the super diagonal, and then lambda 2, and then a 1 here, and so on. So if you're going to take this Jordan, so that's the J. If you're going to take this Jordan matrix and raise it to the n, what actually happens here is very regular. This is basically going to look like, on the diagonal, you're going to end up with lambda 1 to the n, lambda 1 to the n, lambda 1 to the n. And on the super diagonal, you're going to end up with some constant times lambda 1 to the n minus 1, some constant times lambda 1 to the n minus 1, and here some constant times lambda 1 to the n minus 2. Okay, so these blocks will become upper triangular, and this will happen. This will happen for each of your Jordan blocks. So you'll end up, j to the n is a matrix that's going to look like this, with these upper triangular blocks. And then what happens? You do V transpose P times P inverse times j to the n times P times W. Well, all this multiplication, all this post-multiplication, all this pre-multiplication is just applying a linear function to all these coefficients. Okay, you're post-multiplying on the right by something, you're pre-multiplying on the right. So basically, you're going to end up with a linear combination of all these terms of the form lambda 1 to the n, lambda 1 to the n minus 1, lambda 1 to the n. These constants here will also, they will also involve terms in n, and this involves terms in n squared. This is where these guys come from. This you can prove by induction. So basically, if you work it out from there, you sit down and you actually work it out, what happens is, and you multiply everything, you end up with something that looks like that. Okay, that's one way to see it. It's a bit messy to sort of do all this work. The PJs, yeah. So the PJs, let me just take a magnifying glass to this. So you had this block. Let's just look at one block. Lambda 1, lambda 1, lambda 1, and I have a 1 here, and I have a 1 here. Okay. When I do this and I raise it to the n, I'm going to end up with the following. Lambda 1 to the n, lambda 1 to the n, lambda 1 to the n. Here, I'm going to have something of the form, some constants, let's say a times n times lambda 1 to the n minus 1. And here, I'm going to have another constant. In fact, I think it's going to be a as well, times n times lambda 1 to the n minus 1. If it's not a, let's say it's a prime. And here I'm going to have some a double prime, and it's going to be n squared lambda 1 to the n minus 2. Okay? If I raise this to the n, I get that. You show this by induction. Now, I have this post-multiplication, this pre-multiplication. So I get a linear combination of terms of the form lambda 1 to the n, a times n times lambda 1 to the n minus 1, a double prime times n squared times lambda to the n minus 2. So suppose I have something like this. I've got lambda 1 to the n plus, let's just say, an lambda 1 to the n minus 1 plus a prime n squared lambda 1 to the n minus 2. I can always write this as I divide by lambda 1, and I do this. I divide by lambda 1 squared, and I do that. I factor lambda 1 to the n, and I get 1 plus an plus a prime n squared, and that is my PJ. Okay, so this is how these things happen. Okay, so I'm not doing a really rigorous proof. I'm just showing you, if you had to really sit down and somebody put a gun to your head, you can work out all these constants and so on. I mean, this obviously, this is one way to do it. Okay, so that's for that. So at least you have some idea where it comes from. When the roots are not repeated, these polynomials are all constants. This is the case for Fibonacci. When all the roots are simple, these polynomials are all constant. Okay, so let's just come back. Let's just come back to this. So let's look at something. Let's look at something slightly different. There's one more lemma I need. So this is a lemma that's, I think, of independent interest. It was it's an old result. It's an old result. I'm going to state it in a second. It can be, I found it later in journals that go back to the 1990s, but probably it goes back earlier. There are lots of ways to prove it. But the first time I encountered this lemma was in a paper of Mark Braverman in a CAV 2006 paper. He stated it and didn't prove it. And I was very intrigued by this lemma, and so I sat down and proved it. I'm going to show you the proof, which I think is, it's a completely elementary proof, and there are more complicated ways to prove it. And this is going to be essential for the subsequent development. So what is this lemma? I want to have lambda 1, lambda 2, lambda k be complex numbers, be distinct complex numbers, distinct complex numbers. So let me credit this formulation to Braverman. I don't know if you can see, so Braverman 2006, but like I said, this is an older result. So be distinct complex numbers of modulus 1 and with no lambda j equal to 1. So these are complex numbers on the unit circle, but they're all distinct, but you don't have 1. 1 is not, the number 1 is not one of these numbers. Let alpha 1 up to alpha k be non-zero complex numbers. They could be complex numbers. They could be the same. It doesn't matter. They're non-zero. They're not necessarily of modulus 1. And let xn be defined by the summation for j equals 1 to k of alpha j times lambda j to the n. Okay? So I claim the following. The claim is that there exists an epsilon greater than 0. So I want to claim that this sum, actually, maybe I should let you think about this. So you see what we're doing here. We have, let me perhaps draw a picture, let you guys take this in. So we've got numbers, we've got lambda 1 here, we've got maybe lambda 2 here, maybe lambda 3 here, and I don't know, lambda 4 here. Okay, we've got all these numbers. And I'm going to look at the iterates lambda 1 to the n, lambda 2 to the n, lambda 3 to the n, and lambda 4 to the n as n ranges of natural numbers. And I'm going to consider the sum alpha 1 lambda 1 to the n plus dot 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 plus alpha 4 lambda 4 to the n. I want to look at this sum. And what do you think happens to this sum? What kind of behavior might it have?
It either becomes 0 or stays away from 0.
Okay, it could definitely hit 0. And what I want to say is that there exists epsilon strictly greater than 0, such that for infinitely many n, xn is less than minus epsilon, and also for infinitely many n, xn is bigger than epsilon. So infinitely often it goes above epsilon, infinitely often it goes below minus epsilon. Okay? Sorry? I meant the real part. Thank you. And you'll see, I'll drop this hypothesis in a second. Yeah, thank you. I meant the real part. Yeah, absolutely. Okay. Does that make sense? I don't know if you find it surprising. I find this a little bit, when I encountered this, I was a little bit surprised somehow, that you couldn't engineer, I mean, I don't know. If there's only one of them, let's say it's I, then what happens to I? Well, it's here, then it goes to -1, then it goes to, the real part goes to 0, then it goes to 1. So yes, I guess that's true. And I thought, oh, can't you get it to cancel somehow? And well, it turns out you can. So I found that a little bit surprising. So I'm going to prove this lemma. So when do I finish, McCoy? 1230, okay. Right, so, but before I do so, let me just make one simplification. So I claim that we can assume that the xn are real. So I want to say that without loss of generality, assume that for all n, xn is real. And the reason is, to see this, you just let yn be xn plus the complex conjugate of xn divided by 2. So that is going to be the real part of xn. And if you look at the definition of xn, well, that's a1 lambda 1 to the n plus dot 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 plus, so yn will be this, right? It'll be 1/2 times this, ak lambda k to the n plus, and the conjugate is just a1 lambda 1 conjugate to the n plus ak lambda k conjugate to the n. And I simply apply my lemma to yn. Now, yn is always real by construction, and yn satisfies the hypothesis, because now, instead of having just the numbers lambda 1 up to lambda k, I've got the numbers lambda 1 up to lambda k, and then another bunch of numbers like that. If none of those guys is 1, then none of those guys are going to be 1. And if it happens that one of these guys is real, let's say lambda 1 is real, then of course lambda 1 conjugate is equal to lambda 1. But then I simply just put those two together, and a1 lambda 1 to the n, a1 bar, then I just write this as a1 plus a1 bar times lambda 1 to the n. And I've got one less, right? So I regroup and so on. So the yn satisfied the hypothesis, that's what I'm saying. So I can assume without loss of generality that I'm dealing with the reals. Okay.
How do you show that it doesn't cancel out everything?
That it doesn't what?
Cancel out everything. If you have, like, in your original set, lambda 1 and lambda 1 bar.
Yeah.
So
I'm not quite sure what you're saying. If in my original set I've got lambda 1 and lambda 1 bar, then here I will have lambda 1 bar and lambda 1.
So if in your original setting lambda 1 was equal to lambda 2 bar,
yeah,
then there is a possibility that
no, but the coefficient a is a conjugate of the coefficient a1 is a conjugate of the coefficient. The a1 bar is the conjugate of a1, so it cannot cancel. It's the coefficients.
Yeah, but coefficient for alpha 1 may be minus coefficient of alpha bar.
Hang on. So these should be alpha, shouldn't they? I put a's here. I guess this should be alpha. Okay. So what I'm saying is that if this is not if this is identically 0, then of course the bigger thing will be identically 0. And if this is not identically 0, this cannot be all I've done is taken the real part, right? So I mean, my theorem is about the real part, and here I've just written what the real part is. I mean, I've written an expression for the real part.
I think the question is, like, if you have I to the n and minus I, like I is one of the coefficients, and then I on the conjugate coefficient also, then you would conjugate those and it would cancel out.
Okay, so you're saying, so concretely, so okay.
The real part not identically 0, I guess.
Why is the real part not identically 0? Of what? Of yeah, so the original thing would be I guess you're saying you've got I and minus I. So for instance, you're saying lambda 1 is this and lambda 2 is that, and alpha 1 and alpha 2 are just 1 and 1.
Alpha 1 and alpha 2 have to be maybe both I would work.
I mean, there's the theorem, right? We're going to show that it cannot be identically 0.
Okay, but your simplification doesn't it?
Okay. I think the question, whatever it is now, I'll just imagine on it.
Sorry?
What happens if the lambda, maybe I'm missing?
Okay, so lambda 1 is I, and lambda 2 is minus I. Okay, so now what alpha 1 and alpha 2 do you want?
Take them both to be I. The question is, why does yn satisfy the hypothesis in
I
there?
don't zero complex number. They don't have to have any real part either, right?
No.
So what can can't you do the thing to cancel?
Well, so if you look at I to the n plus minus I, say, to the n, if we just take the coefficient to be 1 and 1, right? Okay, what happens here? So initially you get this. So this is I to, so when n equals 1, you have 0. When n equals 2, when n equals 2, I square is minus 1, and minus I square is also minus 1. When you sum them, you get minus 2. And this will happen infinitely often. So you're saying I put, okay, wait, so I put I as the coefficient and I as the coefficient here? Okay, but then when n equals 1, you get I times I, which is minus 1. So that's minus 1. And here you get, wait, yeah, you get minus I, but times I, you get, I see, you get minus, I'm confused, but okay, so you still infinitely often, so you're still infinitely often negative, right?
This is just like shifting it, yeah. So the point is that here for n even, it will give you something real.
Yeah.
And if you add I, then for n odd, it will give you something.
Yeah.
Okay.
Does that make sense? I found myself a little bit confused by this example, but
No. I mean, it just by adding I, you're just changing it for n to n plus 1.
The phase.
You're just changing the phase.
Yeah.
The point is, for some phase, it will give you something real.
Yeah. Yes. Okay, so you want to say, hang on a sec. So I just concretely, I just write it. So you're saying the original lambda 1 is what? Okay, alpha 1 is what? I lambda 2 minus I, and alpha 2 I. Okay. So, and you're worried about this, or when I go to the conjugate, the yn? You're worried about this. Okay, so let's have a look. So this is I times I to the n plus, so plus I times minus I to the n. So when n equals, when n is 1, let's just look at when n is 1. You got I times I, you got minus 1 here, and you got I times minus I, which is minus I squared, which is minus 1, which is plus 1. So you get 0. Okay. And when n is 2, you get I times minus 1, so that's this, plus minus I squared is the same as I squared, which is minus 1. So you get plus I. Minus I. So this would be minus 2I. This is a bit bizarre. Is this right? When n equals 2, I squared is minus 1, so that's minus I. And no, but minus I squared, I'm a bit confused. Minus I is I squared is minus I. Yeah, so I get minus I as well, yeah. Minus I. Oh, I see, so times I. Yeah. Yes, minus 2I, yeah, okay. I see, and the real part is 0, okay. So that is not good. So what is the problem with this? Yeah. Yeah, okay. So I think I tried to cut corners a little bit. I'm going to amend the proposition to say that, yeah, well, minus the counterexample. So either the real part is always 0, and if the real part is not always 0, then the theorem holds. Okay? The theorem said, the theorem said be non-zero complex numbers. So I want to say that infinitely often I'm both negative outside of epsilon and positive outside of epsilon. And the amendment is the real part is not identically 0. Is not identically 0. Okay? All right, are we happy with that? Okay, so yeah, I have time to okay, so let's see where I use this in the proof. So that's going to be interesting. So let me just so we'll see where we end up using this. So the first claim 1 is that for all n, okay, I have that if I look at the sum of n equals 0 to capital N of these xn, so remember what these xn's, I'm now assuming that they're all the xn's are real. So in absolute value, this is bounded by C1 for some real C1. So this is bounded above. For any n, there's a C1 that bounds it uniformly for any n. So this is the running sum. Okay, and the way to see this is to write the sum n equals 0 to n of these xn is in absolute value is less than or equal to alpha 1 times the sum n equals 0 to n of lambda 1 to the n. So I'm going to put absolute value here. I'm going to put absolute value there, plus dot dot dot, plus alpha k times the sum n equals 0 up to n of lambda k to the n. Okay, does that make sense? Which is less than or equal to alpha 1. Now this sum is less than or equal is actually, I can calculate explicitly this from, this is a geometric progression from 0 to n, so this is 1 minus lambda to the n minus 1 divided by 1 minus, sorry, this is lambda 1 plus dot 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 plus, so that's actually equal here, plus alpha k times 1 minus lambda k to the n minus 1 divided by 1 minus lambda k. So here I use the fact that none of the lambdas are 1, so these divisions are allowed. And now this is less than or equal to, well, in absolute value, lambda 1 to the n minus 1, these are all complex numbers of modulus 1. So this top part is at most 2. So this is alpha 1 times 2 over 1 minus lambda 1 plus dot 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 plus alpha k times 2 1 minus lambda k, and I guess I want to put absolute values, but this is by definition this is what I'll take to be my C1. Okay? That makes sense? Okay. Claim 2. Claim 2 is that the sum of the absolute values of any k consecutive xn is bounded from below. So I want to write this as for any n in n, the summation for n equals n plus 1 up to n plus k. Okay, so I'm taking k being the number that I have lambda 1 to lambda k. So I'm taking k of absolute value of xn. And I'm claiming that this is bigger or equal to some C2. So, okay. So I'm claiming that for any n in n, there is, I'm claiming that there is a constant C2, such that for any n in n, this running sum is going to be bigger than C2. Okay, it's bounded below by some constant that's independent of the capital N. Okay. Sorry. K is the same K. I have lambda 1 to lambda k. Yeah. Okay. So to see this, so the proof is going to continue here. I write M to be the following matrix. So I write 1, 1, 1, 1. Here I write lambda 1, lambda 2, lambda 3, lambda k. Here I write lambda 1 squared, lambda 2 squared, lambda 3 squared, lambda k squared, and all the way up to lambda 1 to the k minus 1, lambda 2 to the k minus 1, and lambda k to the k minus 1. Anybody know what this kind of matrix is called? Yeah, this guy's very good. He's going to get an A+. It's a van der Monde matrix. And anybody else know what the determinant of a van der Monde matrix is? There's a very nifty expression for the determinant of such a matrix. Exactly. So the determinant of M is simply the product for I not equal to j of lambda I minus lambda j. I guess plus or minus, but it's given by this the product of these differences, plus or minus. Now, because all these lambda I and lambda j are distinct, it means the determinant is not 0. So this matrix is invertible. Okay, so this is all I'm going to use. So now I look at the following. Actually, let me use the other board. I'm just going to leave the matrix there. Okay, so I have my invertible van der Monde matrix, and I write M times the vector alpha 1 lambda to the n plus 1, alpha 2 lambda to the lambda 1, lambda 2 to the n plus 1, dot, 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 alpha k lambda k to the n plus k. That is equal to, thanks very much. That would be plus 1, yeah. So can somebody tell me what vector I get once I multiply my matrix M by this? Yep. I get x sub n plus 1, x sub n plus 2, dot, 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 x sub n plus k. That's right. And so I have that and so another way to write this is that I can write the vector alpha 1 lambda 1 to the n plus 1, alpha k lambda k to the n plus 1 as M inverse of x1 up to, not x1, I mean xn plus 1 up to xn plus k. Okay. And now the natural thing I can do is take the one norm on both sides. So the one norm is the sum of the absolute values. So if I take the one norm here, I get, so I'll take the one norm here, which is the one norm here, okay? And this is less than or equal to, by the property of the one norm, this is less than or equal to the one norm of m, which is simply the sum of the absolute values of the coefficients of m, times the one norm of x n plus 1 x, sorry, there's a one norm x n plus k, okay? And this is, of course, equal to the one norm of m times the summation of the absolute value of xn for n equals, for little n equals n plus 1 to n plus k by definition of the one norm, yeah? So this expression is bigger than this. So I can say that this is bigger. I'm just rewriting it here. It's bigger than or equal to, sorry, the one norm of that, right? Which is the one norm of, I'm going to write it here, alpha 1, lambda 1 to the n plus 1, alpha k to the lambda k to the n plus 1. Okay? So I divide by this. And erase it here. And I have that this expression here is bounded below by that, and I will call this my constant C2. Okay? This cannot be 0 because these guys cannot be 0, and the one norm is a sum of absolute values. Yeah. It appears to depend on n, but it doesn't because, yeah, that's a very good point. So that's not quite right. Thanks very much. I'm going to do one more step. So this expression I'm going to write as the yeah. So what is this expression? This expression, yeah. Thanks very much. This expression is the summation here of alpha 1 times lambda 1 to the n plus 1 plus plus alpha k times lambda k to the n plus 1 divided by the one norm of f inverse, right? Okay, but these guys are just 1. Okay? So I just have the summation of the alpha of these guys, and this is what I call my C2. And I think this is where we're assuming that this is probably where we're assuming that the thing is not always 0 somehow. Oh no. So no, of course not. These alpha I they're just not 0 themselves. Yeah. So far I still don't see. Okay. Does this make sense? Okay, we're happy with that. Okay, we're almost there. So I have these two claims, claim 1 and claim 2. Therefore can erase this board. And the punchline is now as follows. So choose a number t such that choose t such that, so t is a number such that t times c2 is bigger than 4 times c1. Then for all n, I mean you work these things out backwards afterwards, obviously. Then for all n as natural numbers, I can write the sum of n equals n plus 1 to n plus k times t, or let me write t times k, okay, of xn is equal to the sum for n equals 0 up to n plus kt of xn minus the sum n equals 0 to n of xn. And I claim that this is at most 2c1 because that's a running sum of xn, and that's another rambling sum of xn. And I know in absolute value, these guys are bounded by C1, bounded above by C1. Okay, so I've got two of them, so it's bounded above by 2C1. So this thing is bounded above by 2C1. This guy goes from 0 to something. This guy goes from 0 to something. So that's bounded by, upper bounded by C1. That's upper bounded by C1. So their sum is, the sum of these two is at most 2C1. Yeah, of course, but, so a fortiori the sum, yeah. I mean, yeah, a fortiori the sum. The difference. I mean, this is certainly an upper bound to these things, right? Okay, so now I write the summation of n equals n plus 1, n plus tk of, I look at the absolute value of xn, and so this is equal to the summation I equals 0 to t minus 1 of the summation n equals n plus ki plus 1 to n plus ki plus k of xn. Okay, I'm summing from n plus 1 to n plus tk, and I'm splitting this as t sums of the form n plus ki plus 1 to n plus ki plus k. So I'm going in k increments t times. So these two sums are the same. And this is bigger or equal to, well, we know that each of these sums are going in k increment every time. We know that this is bounded below by C2. Each of these is bounded below by C2. So this is greater than or equal to 2C2, which is bigger than 4C1. So if I take the sum from n equals n plus 1 to n plus, how did I write this? N plus tk of xn, and I only sum over those xn that are negative, I claim that this is less than minus C1. Okay, so what am I saying? I'm saying that when you look at this sum is going to be summing over numbers that are negative and numbers that are positive. In aggregate, I know that when I sum all these numbers, the positive and the negatives together, I'm below 2C1. When I sum the absolute values, so that includes all the positive numbers, plus the negative numbers that have been made positive, this is bigger than 4C1. So I'm claiming that if you sum over just the negative numbers, you're going to be below minus C1. Otherwise, you immediately, derive contradiction. Does everybody see this? I'll let you stare at this for a sec. I mean, it just needs to be looked at. So this is here. I'm just summing over the negative numbers. And because when I sum over all the numbers, I'm less than 2C1. When I sum over the absolute values, this consists of the positive numbers, along with the negative numbers that have been upped. I need my negative numbers to bring me, push me up like this. So the negative numbers have to be sufficiently large. Okay, I'll just leave this for now. I mean, just follows from these equations. And so I'm done, because what happens now? I've got k numbers. I've got x n plus 1 plus x n plus 2 plus ... plus x n plus tk. Okay, and I know that this is less than minus C1. So I know that at least one of these guys, above, sorry, I'm just summing over the negative ones, sorry. Only only the xn that are negative, less than 0. So I'm summing amongst all these xn's, I'm only keeping the ones that are less than 0. And I know that together they go below minus C1. So I'm saying that at least one of them, so must be some xn, so there exists an n in this range, n plus 1 to n plus tk. At least one of them must have the property that xn must be less than minus C1 divided by tk. Because if they're all bigger than this, then I wouldn't be able to achieve this this sum. Well, I'm done. Take this to be my my epsilon. Okay, I've shown that there is one n that goes below this thing. These constants t and k are, k was given to me, t was found at some point, and C1 was also found. So this is actually a constant that's independent of the little n. Okay, does that make sense? Okay, sorry I made more of a mess than I thought I would. To show that it infinitely goes above epsilon infinitely often, you just consider a sequence minus xn, you do everything, and you show that the sequence minus xn goes below epsilon, and by symmetry, you're done. Right, okay. So